So homework 27 is page 493, section 8.1. Yes, we are going to jump into chapter 8 for one section and then go do a bunch of other stuff like I said last time. So section 8.1, numbers 3 through 9 odd, 15 through 19 odd, 23, 25, 27 through 39 odd, 45, 47, and 51. So last time we talked about how U substitution is the inverse of the chain rule. In other words, you have some function that's composed with a function, you take a derivative, there's a certain thing to do, we call that the chain rule. To undo that, we do U substitution. So what's another rule? We have the chain rule for differentiation. What's another rule that you think we might undo today? If you said the quotient rule, get out right now. Just go away, never come back. You're banished from the riches of my kingdom. This bears repeating, okay? Quotient rule is just the product rule in disguise, okay? So if you have some function divided by another function and you take its derivative, it's the same thing as taking the derivative of the function times the bottom function to the -1. And now you could just see that as a chain rule, right? Because it's something times something. And so you take the derivative of something times something, and we say, okay, take the derivative of the first thing, leave the second thing alone, add that to, leave the first thing alone, take the derivative of the second thing. So the -1 drops down, and then we decrease it down to -2. Leave the inside stuff alone, multiply by the derivative of the inside stuff, which we could see as the same thing as f prime over g. Now that's a -1, so that's going to be minus fg prime in the numerator. Divide that by g squared, right? To get a common denominator, we multiply the top and the bottom here by g, giving me a g squared and a g up here, or lo and behold, that's the quotient rule, right? And so really the quotient rule, this is a special case of the product rule. It's where in the case where the product, the thing is raised to the -1, you could realize that as a quotient and then derive a quotient rule, but it all follows from the product rule. So can you guess what rule we're going to undo today? Yes, it's the product rule. So let's get that up here on the board. So recall, if you have a product of two functions, f times g, and you take its derivative, we take derivative of the first thing, leave the second thing alone, add that to, leave the first thing alone, take derivative of the second thing, right? And now we want to undo this, right? Now, well, here's the tricky part. This notation is not going to help us get to something that will be actually useful. But we could see, like, if you basically what I'm saying, if you integrate this side, that's the antiderivative of a derivative. And so that's just whatever you started off with, right? And then here, I mean, this is just f prime g plus fg prime, or you could break that up into two integrals, f prime g plus integral fg prime. Problem with this, though, is this doesn't, again with the prime notation, this doesn't help us like actually apply this unless you happen to have, unless you're trying to take the integral of something that looks exactly like this, and you recognize, oh yeah, that's like the derivative of a function times a function. Oh, and that's the derivative of that. But again, this doesn't really help us, especially since there's no dx involved or a differential somewhere. And we saw how useful that was last time, being able to change your du and your dx and relate those guys together. We want the same kind of thing here. So instead of using prime notation, what I say we do for this the product rule here is, let's use the D notation. So And another thing, instead of using f and g, we're going to use two functions u and v. I'm just going to go ahead and skip right to that because this is the way everybody teaches it. Same way it's always u substitution and not t substitution. We always use u and v when we're learning this stuff, just the way it is. So let's say we have two functions, u times a function v. And of course this could be a u of x and a v of x. It might be of t or whatever. It doesn't matter. That's why we're not putting the name there. And this is what the d notation is going to help us do. So, okay, we take the derivative of this stuff here. D, that stuff. Well, then that's the derivative of the first thing. So that would be du, leave the v alone. Add that to leave the u alone, take the derivative of the second thing. This is the same thing as saying u prime v plus uv prime right there. But now we're just using d instead of prime, okay? And what I'm going to do, since we know that this has to do with integrals, I'm going to rewrite this as v du plus u dv, like that. Everybody buy that? Everybody believe that? You can check it right here. D just means the derivative of. It's just like prime, okay? And so now, when we undo this, when we take the integral of both sides of this, let's see what happens. Integrate this whole, and now here I'm integrating this entire thing. So this is the antiderivative of a derivative. This is just uv plus a constant. I'm not going to bother with that. And here on the right-hand side, I'm going to go ahead and break this up into two integrals. V du plus the integral of u dv. Now, as it's written here, this is actually not very helpful, because again, we're kind of in the same situation. It's like, okay, so you're telling me that if I have an integral that I could split up and I could recognize part of it as the derivative of one, and then the other part, this part of that, the derivative of that part. So I guess if that's an x squared and you just have a 2x there, and if that's maybe a sine, then over here you have a cosine. Again, lots of guesswork there, and it's kind of like, if you remember when we had this, and we're trying, and it's like, okay, how can I, if I have an integral I'm trying to figure out, then I guess this might be like this. If it just so happened that your thing worked out, then yes, you might be able to match this stuff up right here and say, oh, and here's that part. Right there. But again, that's really hard to do, right? We learned a better way of trying to mix and match all of this stuff. We're not going to mix and match here. In fact, what I'm going to do right now is rewrite this in a way that's actually going to help us. And what I want to do, I'm going to subtract this over, so we get uv minus the integral of v du equals the integral of u dv. You might think, okay, it still looks bad. I'm going to be mixing and matching. But the idea now is what we have. Is given something like this, if you can find a u part and a dv part in the integral that you're given, now we have a way of rewriting this. Now you might be wondering about constants, because of course what I didn't write here is you take the antiderivative of derivative. Well, there's a constant here, and so if we were keeping track, we could say, okay, there's plus a c1 there, and then, and like I said, the idea is you're given something like this, and we're going to use this, and so we could say, well, then there's another constant that comes out here, and so then we'll absorb all the constants, but you'll see how this will work when we actually go to do it. We're not going to worry about taking care of the constants until the very end. And right now, this is the bit that we care about. And I'm going to go ahead and write it this way, where we're going to start with u dv equals uv minus the integral of v du right there. Because we usually think of the thing that you're given, the thing that you want right there, instead of this way around. And so, let's see how we're going to actually use this. So, just one note to make. You might say, it looks like you're taking something simple and making it more complicated. But the idea here is that in practice what you're doing is this U part and this dv part, usually this U part is something that's going to be easy to take a derivative of, or something that gets simpler when you take its derivative. So for instance, if U is x squared, du is going to be something that's simpler, something that's easier to deal with. dv, on the other hand, this will help us if this is something that's easy to take an antiderivative of. Because you could see over here, right, if taking the antiderivative of dv, the antiderivative shows up right there. And similarly, so if u is something that's easy to take a derivative of, or something that gets simpler as you take a derivative, like this, then when it shows up here, now you have an integral of something that's simpler. We'll do plenty of examples where you'll see exactly what I'm talking about, but this is the idea behind this, and you'll see its utility here in just a minute. So, here's an example. We want to find the integral of x sine x dx. One telltale sign that you want to use integration by parts, and by the way, this is called integration by parts. IBP is what we're going to call it. That is integration by parts. You can see it's like parts, right? There's one part, there's another part. Okay, anyway. Okay, so one of the telltale signs that you might want to use integration by parts is when your integrand has a product in it, right? It's like we see with a product rule, you end up with products, right? A product of a derivative times a function, product of a, And so it could very well be the case that when you see a product in your integrand, you might want to try integration by parts. This might be the product rule in disguise. And so what we're going to do is assume that part of this is u and part of it is dv. And the way I like to organize this stuff in my head is whenever I'm going to do integration by parts, I go ahead and write down u, du, dv, and v. And the idea is I'm going to choose some part of this to be my u and some other part of it to be my dv. Okay? Just like this. And in general, what you do is you choose the thing you choose it so that it gets simpler as you take a derivative. This is not always going to work, but because that's kind of what I'm going with, I'm going to say, okay, well, let's let u be the x part here. So then du would just be dx. Okay? Now, everything else, everything that's not x, has to show up right here. So then the rest of this must be my dv, which would be sine x dx. And say, okay, if that's a derivative, then what is its antiderivative? Should be minus cosine. Like that. And I'm just going to check. If I have minus cosine, I take the derivative. Cosine goes to negative sine. So negative, negative, yes. Okay, so we're good to go. Now, I'm just going to fill in this formula right here. Okay? I'm going to say this is the same thing as uv, and so that's going to be x times negative cosine x. So how about negative x cosine x? There's my uv. Minus the integral of v du, right? So minus, now it's a minus minus, so I'm going to pull that minus out front and say plus cosine x, that's my v. The du is just dx. Okay. This looks much simpler. Now, we have a different integral, but it is an easier integral to deal with than the original one that we started off with. And that's what I was saying, is that's where the utility is here in this. You're like, well, the right-hand side looks more complicated. It's like, yes, but this integral on this side is more complicated than this integral on this side. And now we could just say the integral of cosine should be positive sine, I think, right? So minus x cosine x plus sine plus a constant. And that's where we're going to end up absorbing all of the constants, right? Like, yes, it's true that a constant came along here, and then a constant's going to come out of here, but we could just bring all those constants together, and that's when I bring in a constant right there, if I'm doing a indefinite integral, which is what this is. Okay, so now, apparently what we have is that the integral of this, or you could say the antiderivative of this function, is this right here. Let's check it. Okay, so I'm going to take, there's negative x cosine x plus sine x plus a constant, take its derivative. Now here, that's a product rule, okay, so it's going to be negative, I'm going to do the product rule, derivative of x is 1, leave cosine alone, add that 2, leave x alone, take the derivative of cosine, and we get negative sine. Okay, now plus sine, the derivative of sine is cosine. Derivative of c is just that, so we have, bringing that minus through, I have minus cosine x, minus a negative is just positive, so that will be plus x sine x, plus cosine x. The plus and the minus cancel, and we're just left with x sine x, which is what we expected, because that is my integrator. Now let's say, it's going to take a lot of experience, that is many times doing this, before you get a feel for what to pick for your du, or for your u and your dv. Okay, and you will mess this up a bunch of times. Let me show you what happens if you make a poor choice. So let's say that we chose the other way around. Let's say I saw this and thought, hey, sine, that's a real easy thing to take a derivative of. So, okay, there's sine x. And everything else then must be dv, so that the rest would be x dx. I say, okay, take derivative of sine, goes to cosine, real simple. I feel good about that. Now, what's the antiderivative of x dx? Well, I guess it would have to be x squared, but then the 2 isn't there, so we'd have to divide. So there you go. Now, you say, okay, so this is going to be the uv minus v du. So uv is going to be 1/2 x squared sine x, right? U times v was that. I just wrote it the way we normally do. Minus the integral of v du. Oh, and look what I didn't do. That'll help you, right? Making sure you're keeping track of your dx's and stuff like that. Just like with u substitution, you take a derivative, you always apply the chain rule. So the derivative of x is dx, okay? Now, you see that you went from an integral like this to one like this. It looks like you made your life more complicated. You could keep going from here and do another u substitution on this, and you'll probably be chasing your tail for a while. And you know, you might get somewhere with it, but the point is, you just went from something less complicated to more complicated. The idea behind this is to take the integral that's more complicated and if it can be broken down into something that's less complicated. Here we made it more complicated, we made our lives worse. So that's something you want to try to avoid. Okay, I'm going to put one up on the board, and I want you to pause the video and actually attempt this one. And of course, yes, it's going to be integration by parts. So let's see what happens with this. E to the x, and we'll do sine x dx. So pause the video and try this one. So, okay, let's just try. We need a u and we need a dv. Okay? Either way we do, really, both, it's going to be about the same regardless of what you choose to be what. So what I'm going to do is I'm going to say the u is going to be the e to the x. The dv is going to be my sine x dx. So my du is going to be the derivative of this, which is going to be e to the x dx. My v is going to be the antiderivative of this, which should be, I think, minus cosine, right? Negative cosine goes to positive sine. Yes, so minus cosine x. Okay, here we go. So, doing this substitution by parts, we get, okay, uv is that times that. So I'm going to put the minus out front. I'm going to go minus e to the x cosine x minus the integral of v du. So that's a minus. The minus is going to come out and make that positive, and we could just write all of that like this. Make sure I got that right. V is the cosine, du is that. Of course, I just switched them around. It doesn't need to be in any order, right? I just put the e up front. That's cool. And the minus came out to make that. Okay. Now what? Well, this is pretty much the same thing as this. It's almost exactly the same. And so I'm looking at that and I'm thinking, okay, u substitution? Well, u substitution's not going to help. Because, I mean, I could guess I could let x be u, but then we'll just have e to the u cosine u. That's not going to help. The integrand still looks like a product. Maybe I'll do u substitution again. And so let's try it. Let's see what happens if I do another u substitution. So here we go. U, I need a u, and I need a dv. Okay, let's do the same old trick. U is e to the x. dv could be cosine x dx. Okay, so then du is going to be the derivative of this, which is e to the x dx. Antiderivative of this should be sine x. Yes, take derivative of sine, you get cosine. Okay, and so I'm going to replace this here, and I'm going to give myself a little bit more room. When you're doing this, you're going to run into ones where you have to do repeated u substitutions like I'm doing right now. And when you do, it's going to be real easy to just focus in right here and forget all about this guy. Be really, really important that you keep track of everything in this line. And so that's what I'm doing right now. I'm writing this here. And now, plus all of this stuff right here is a new integration by parts. So I'm going to go ahead and do this thing here so that I don't mess this up. So now, here's this integral right here is going to be uv, so e to the x sine x minus the integral of v du. So that times that. So I'm going to write that as e to the x sine x dx. Now I can see, okay, I did this well, I didn't have any constants. I could go ahead and drop these guys right here. Let's say this is that. Okay, now let's deal with this. Uh-oh. This is what we started off with, isn't it? And I could go ahead and do it again, but guess what's going to happen? We're going to get the same thing. And you could just keep plugging that in and get this just string of stuff that's just going to keep going on forever and ever and ever. And it's like, well, what are we going to do here? Well, let's just think for a second about what this says. Okay, forgetting about all this work we've done, what we just had was we had some integral, e to the x sine x dx, and apparently it's equal to negative e to the x cosine x plus e to the x sine x minus the exact same thing, this thing, e to the x sine x dx. Any ideas of what to do next? One thing you could do, and this is not necessary, we could just do this without this next step that I'm going to take. But oftentimes it's nice to think about think about this and say, you know what? This is something. This symbol right here is something. Let's give it a name. Let's say it's I for integral. Okay? That's some I. Then we can replace this. We can say, okay, then I equals some function cosine x plus e to the x sine x, like that, minus, I again. If I told you to solve for I, what would you do? You'd probably say, well, let's get all the i's on one side, so I'll add him over here. So that's I plus I, or in other words, 2I is equal to minus e to the x cosine plus e to the x sine. And it's I, we want to get I by itself. So it looks like we're going to have to divide by 2. So I'm going to do that. I'm running out of room here, so I'm going to do something like this. This is the same thing as if I divided both sides by 2, giving me minus e to the x cosine plus e to the x sine all over 2. And that is that. So we got it, don't we? In fact, what this should be this thing right here. It should be the case. That should be the value that we want. So let's check it. If that's, plus a constant, right? So if that's true, right, then I should be able to take the derivative of this and I should get e to the x sine x. So let's do it. Let's do it. Let's get a little bit of room up here. Alright, so here's this thing. I'm going to rewrite this a little bit. I'm going to write this as 1/2 times this stuff. Negative e to the x cosine plus e to the x sine. I'm being lazy, obviously. I'm not writing my x's and stuff like that. Okay, so take the derivative of that. The 1/2 is going to stay way out there. So I'm going to give myself a bunch of room, and the 1/2 is just going to come along for the ride. Now, this is a product. So it's going to be negative a bunch of stuff when I do the product rule. Take derivative of that, leave this one alone. Add that to, leave that one alone, take the derivative of that. So leave that alone, you get negative sign, and you take the derivative of that, so I'm going to bring my negative out there. Okay? Now, add that to, I'm going to do this part, it's a product, so I'm going to do this, and say, okay, take derivative of e, leave sign alone. Add that to, leave this alone, take the derivative of sine, it goes to positive cosine. Okay, so now we have 1/2 times. Now let's get all these through. So that's minus e to the x cosine, minus is plus e to the x sine, This is all just plus, so that's plus e to the x sine plus e to the x cosine, all in my bracket. Now minus and plus are gone. E to the x sine, e to the x sine. That's the same thing as 1/2. There's two of them. There's two e to the x sine x's. A half and a 2 cancel, and I get e to the x sine x, which is indeed what that was. Here's number 34. Try it. Pause the video and try it. Okay, here we go. Now let's just say that you didn't read the instructions for this part on number 34, and you're like, all right, let's just go for it, see what happens. Okay, so product, I guess we're going to go, here's a u, here's a dv. So choosing my u, well, I guess t cubed will get simpler when I take its derivative, so I'll do that. So du is then 3 t squared dt. Everything else must be e to the negative t squared dt. And so the antiderivative of that is, good luck. You're never going to figure that out. There's no closed form for that. So you'd make your life much harder if you did that. So you say, okay, I'll do it the other way around. And that's kind of the cool thing, is if there's something you can't take the antiderivative of, well, put it here. We can take the derivative of that. So let's do that. So the derivative of e to the negative t squared is going to be e to the negative t squared times the derivative of the inside stuff. So that's minus 2t, I guess, right? Because negative 2t squared, the derivative is that. And so, okay, so I'll write that as minus 2t e to the negative t squared. Now the dv is everything that's left, so t cubed dt. So its antiderivative must be t to the 4th, but we're going to need a quarter out of there. Okay, so we're just going to try this and see what happens. So this is uv minus the integral of e du. uv, that's a quarter t to the 4th e to the minus t squared minus the integral of v du. Okay, so let's see. The quarter and the 2 come out to a half, so I'm going to just bring him out front. The negative makes this positive. So you see, I'm taking care of my constants first. Now we have a t4th and a t, so that's t to the 5th.
Hello, let's play together.
E to the minus t squared dt. I didn't write my dt. Bad form, Justin, bad. Okay, so what just happened? We had this and we turned it into, is this more complicated than that? Yeah, a lot more complicated. It's, I mean, by a factor of 2, or by a power of 2, right? Like, I don't feel very good about this. So, what do we do? There's really only 2 things we can choose to be u and dv, right? We can either do this one here or there, right? And so now we just made our lives more complicated. It looks like we're going to have to do another similar thing. This is just as part of it. You run into this all the time. You're like, well, I made it more complicated, so maybe I'll switch these guys around. You go switch them around. And when we did that initially, there is no way to take an antiderivative. So what do? Well, you read the problem a bit more carefully, and it tells you to first make a substitution and then do integration by parts. And so, now here's the thing. Normally we use u for a substitution. In fact, we even called it u substitution. But now we have a new formula with u and v, so it's going to be easier if I make a substitution that's not u. I'm going to do a u substitution, but I'm not going to use the variable u. In fact, I'm going to use the variable x. I'm going to say, okay, let's let x equal something. And again, now if you were just dealing with this one right here, right, before and pretending that we didn't know we were dealing with integration by parts today, you'd probably look at that and go, ooh, look at that. I have a function inside of a function. Maybe I'll now do a substitution and say let u, or x, be the inside stuff. So negative t squared. So that dx equals, let's see, negative 2t dt. So that now my dt is equal to dx over negative 2t. And we go and plug that stuff in, and let's see what happens. So here's t cubed e to the, now it's to the x. dt is now dx over minus 2t. Okay? So 1t cancels, and we have a negative, so I'm going to pull out the constant, negative 1/2 out front. Integral. One of those cancels one of those, so now we have t squared, and then everything else is dx dx. And it's like, uh-oh, we didn't get rid of all the t's. It'd be nice if we got rid of all those t's. So, if you remember a bunch of these in your homework last time, you say, whoa, wait a second, look at that. There's t squared, there's a t squared. And so, negative x is t squared. Or, I mean, we could bring that guy in, whatever, right? But I could say, okay, this gives me negative x is equal to positive t squared right here. Just multiply both sides by negative 1. And so t squared is going to be negative x. So negative 1/2 integral negative x e to the x dx. Negative, I'm going to pull them out and make that 1/2 x e to the x dx. Now what do you do? Well, now you're going to look at that and say, okay, hold up. U substitution isn't going to help. I don't really have anything inside of anything. If I let that be u, well, that's just u, right back where we started. And so I see a product. I see e to the x times x. Maybe I'll do a u substitution. I'll do integration by parts. So I'm going to go ahead and get rid of this stuff just to give me some more room. We just found that this, with this substitution, gives me that. So I'm going to say this is the same thing as 1/2 the integral of x e to the x dx, like that. Now, I have a product. So, I'm going to try parts, integration by parts. And so, again, I could go either way here, but I know that if I let my dv be x, it's going to get more complicated. And so I'm going to let x be u here, so that when I take its derivative, it gets simpler. And then the resulting integral that I have will be simpler. Also, e to the x, the remaining stuff, it's easy to take its antiderivative. It's just e to the x. So, now, and here, be very careful, because now we have a constant up front. Okay, so it's going to be that constant times this stuff. Here, parentheses or brackets are going to be your best friend. So that's uv minus v du, minus the integral of v du. Okay, so uv is going to be x e to the x minus the integral of v du. Oh, I just made my life a lot easier, didn't I? That's a lot easier. Okay, that integral is easier than that integral, so we feel good about this. So that's quite simple to do. This is 1/2 times x e to the x minus antiderivative of that is just e to the x plus a constant. Now we just distribute that half and let's see what we get. That's 1/2 x e to the x minus 1/2 e to the x plus a half of a constant. It's still just constant, so we should be good there. But they didn't ask about x, did they? They asked about t. So now I'm going to finally bring my t back in and say that's 1/2 negative t squared e to the negative t squared minus 1/2 e to the negative t squared plus a constant, which I could rewrite as negative 1/2 t squared e to the negative t squared minus 1/2 e to the negative t squared plus a constant. And that should be my answer. Let's check it real quick. Okay. Okay, boy, lots of work for that. Okay, so I'm going to take the derivative of this. 1/2 is going to come along for the ride. We have a product. So, 2t e to the minus t squared plus, leave the first part alone. The derivative of this is the thing. Then we multiply by the derivative of the inside stuff right there. There's that part. Minus 1/2 times the derivative of this. So the derivative of that is the thing, e to the minus t squared times the derivative of the inside stuff. The constant goes away. So now we have minus, that half comes in and kills that, t e to the minus t squared. The half comes in, kills that, negative negative makes it a positive, and we have t cubed e to the minus t squared. Okay, minus minus is a positive. Half and a 2 are gone, and we have t e to the minus t squared. T e to the minus t squared minus e to the minus t squared, blah blah blah, gives me t cubed e to the minus t squared, which is what we started off with. Check. For number 20, we have a definite integral, and it should come as no surprise to you that I do it a certain way. Now, it's true that if you have a definite integral from, say, a to b of u dv, it is the same thing as uv minus integral v du, where you evaluate them at the same endpoints, right? A, b, there. And here, since that itself is an antiderivative, you would evaluate it up at b and down at a, right? So that is, whatever uv is, you would plug in the ub v b minus u a v a, right? But what I do, should be no surprise, I just keep going until I just find the antiderivative and then do all of that, okay? Now, when I look at this, we're going to do this one two different ways. Because when I look at this, my initial, my intuition is to say, well, you know what, I could distribute this in. And I would have 0 to 1 x squared e to the negative x plus e to the negative x like that, which I could then break up into two integrals, and that one's easy to deal with. And that one looks like we need to do some kind of integration by parts. And so let's just go ahead and do that. So here's from 0 to 1. Okay, that one's easy. Like we said, that should just be negative e to the negative x. That should be the antiderivative of that. So we're going to evaluate it up at 1 and 0. Okay. Now this part, here's the hard part. 0 to 1 x squared e to the negative x. And for this, I'm thinking, and of course I didn't bring my dx along for the ride. Sorry, everybody. I'm thinking, okay, I have something times something. You might think u substitution, but if you substitute x squared for u, then that's going to be root u. That doesn't look too good. So I'm thinking integration by parts here. And so I need a u. And I need a dv. The u I'm going to choose to be the thing that gets simpler as I go. So I'm going to say that's x squared du. So the derivative of that is 2x dx. Everything else is my dv. Antiderivative of that, like we already said, was minus e to the minus x. Check it. Take derivative of that, goes to that. The negative comes out. Negative, negative. Okay, good. Okay, so here we go. This is now uv minus v du. So, uv, so how about minus x squared e to the negative x, that's u times v, I just pulled the negative out front, minus the integral of v du. So there's that. So I have a minus and a 2. I'm going to pull both the minus and the 2 out to make that a positive, and a 2 comes out front. What's left is x e to the negative x, x e to the negative x dx. This guy is still coming along for the ride. E to the minus x evaluated up at 1 and 0. And oh boy, we're back. We got another one to do now, don't we? Because that's still a product. So I'm going to go ahead and do it again and say, okay, u, I need a dv. The u is going to be the thing that gets simpler as we go. So it's x, du is dx. Everything else, e to the minus x dx is my dv. The antiderivative of that would be minus e to the minus x. Yeah? Yeah. Now here's where it's going to get really ugly, because it's 2 times some stuff, and then we have a minus other stuff. We're going to have to make sure, again, parentheses or brackets are your best friend here. This is the thing I'm about to rewrite. And so I'm going to do some brackets here. Plus 2 times whatever this works out to be, minus e to the minus x evaluated at 1 and 0. Okay, so now we're going to use this to get our new uv minus v, blah, 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 blah. So uv is negative x e to the negative x minus the integral of v du. There's the minus, so the minus comes out as a plus. V du is that guy. One second. Did I do this right when I did that? Minus, yes, okay. Sorry. Just making sure. So v du, I already pulled the minus out, so all we have left is e to the negative x dx, and that's an easy one to do. So here we go. Minus x squared e to the minus x plus 2 times minus x e to the minus x. The antiderivative of that should be negative e to the minus x. Okay. So now we have a 2 has to come in. Did I do that right? Yeah, I did that right. So altogether we have minus x squared e to the minus x minus 2x e to the minus x. Positive is minus 2 e to the minus x. Finally, minus e to the minus x. And this is again evaluated at 0 and 1, but now we're evaluating the entire thing. This is my antiderivative. And I'm evaluating it from there to there. It's the entire thing that we're evaluating up there. And so, like, I could have done that way up here, found out whatever number that is, and brought him along for the ride. Doesn't matter. I could do it right now individually, but one thing I notice is I could combine these guys a little bit. Doesn't matter how you want to do it. So, minus x squared e to the minus x minus 2x e to the minus x. Now we have 2 e to the minus x's minus 2 e to the minus x's minus another one, so that's a total of minus 3 e to the minus x at 1 and 0. Okay, plug in a 1, and I get minus e to the minus 1 minus 2, 1 e to the minus 1 minus 3 e to the minus 1 minus, when I plug in a 0, this is nice because he goes away, and all I'm left with is minus 3 e to the 0 is just a 1. So that's that. And here we go. So there's minus 2, minus 3, so that's 3, 4, 5, 6. So minus 6 e to the negative 1s. Minus a minus is plus 3. That should be my answer right there. You could write that as 3 minus 6 over e. A couple different ways of writing it, okay? And so that's the answer I got that way. But like I said, it might, oops, negative 1 plus 3. It might be easier, instead of breaking this up, it might be marginally easier to do it a different way. And like I said, my intuition says if you can get the integrand, you know, the same way that, like, if you have something like this, x squared plus 1 times x minus 2, it might be easier to just go ahead and multiply it all out and do it individually. That was my intuition right here, right? Multiply it out and do them individually. Well, let's just see what happens if we don't do it that way here. So I see, okay, I have a product of stuff, u substitution. I would think to substitute u equals that, right? Like x squared plus 1, which then would give me du equals 2x dx. Then that x is going to have to be, I guess, u minus 1 equals x squared, so that x is root plus or minus u minus 1, and then you have to figure out, is it the plus or the minus when it's from 0 to 1. Then I have a root, e to the root. That doesn't seem easier to deal with. So I don't want to go down that route. Let's just do this. We need to choose a u, choose a dv. Let's let u be the thing that gets easier as you do it. So we're just going to go for broke and say, let's let this whole thing be u right there. My dv is my negative x dx. So my antiderivative is this. And then this guy is just 2x dx. So now we're going to say, this is the same thing as uv, so negative x squared plus 1 e to the negative x minus the integral of v du. That negative could come out front like that. Du, 2 could come out front. And now we're left with x e to the negative x dx. And again, we're kind of in this situation one more time, right? Where we say, same type of deal. We're going to need a u and we'll need a dv. So my u is going to, I want the thing that gets simpler when I take its derivative. Everything else is dv. Its antiderivative is that. So now we have negative x squared plus 1 e to the negative x plus 2 times, okay, uv is negative e to the x times x, so negative x e to the negative x minus the integral of v du. The negative comes out, e to the negative x dx. Looks like this one's a bit more simple. Not by that much, but it's a bit more straightforward. So this is nice. X squared plus 1 e to the negative x. Now, this is the same thing as negative, I'll just do this. X e to the negative x. Antiderivative of that is negative e to the negative x. Just like that. Plus a constant, but we don't care about the constant because we're evaluating endpoints. So negative x squared plus 1 e to the negative x. So that's minus 2x e to the negative x minus 2 e to the negative x evaluated at 1 and at 0. 1 and at 0. So when I plug in a 1, I get, that's negative 2 e to the negative 1. Minus 2, that's a 1, so minus 2 e to the minus 1. Plug in a 1, I get minus 2 e to the minus 1. Minus, what happens when I plug in a 0? Well, he goes to 0, but now he's a 1. So that's a 1. E to the 0 is 1. Minus 2. Oh, that was a minus, wasn't it? I messed that up. So that's a minus 1. Minus 2, plug in a 0 here, he goes to 1. So minus 2. So that's minus 2, minus 4, minus 6, e to the minus 1s. Minus, that's a minus 3. Minus 3 is plus 3. And we get the same thing we got the other way. I think this way was a bit more straightforward. So, but either way you do it, it's about the same. So, just something to watch out for. So definite integrals, I do exactly the same way. I just keep going until I have found the full-on antiderivative, and then I plug in evaluating it at the endpoints. Okay, let's do this one. We want the definite integral of log x from 1 up to e. So what we're trying to do here, let's just think about this. Log x looks like that, right? Natural log. And 1 is right here, and e is right there. And what's the output? What happens when you plug e into log? You get out a 1. Okay, so this is the area we want right there. That's what this represents. That's that area, the area under that curve from 1 to e. The hard part is finding the antiderivative of log, right? And this will mess you up every single time you do it. Because you look at that, and at first you go, wait, it's 1 over x. No, wait, the derivative of e is 1 over, I mean, the derivative of log is 1 over x. And so, then you look at that and you think, okay, use substitution. That's not going to help. Like, let's let x equal u, and then, oh, now we have log u du. That doesn't help. And then you think, well, I guess it's the only other thing I know how to do, integration by parts. There's not a product. Oh man, what do we do? And so then your mind starts cranking, and you're thinking, well, what if I do this, and what if I do that, and what if I do this? This is one of the things. This is the takeaway thing about from this whole example is integration by parts. Actually works in situations where it might not look like it does. Okay? So, for instance, it doesn't look like there's a product of something in there, but there is, right? There's this, and here's this. And so, it's pretty obvious what one of them should be. So, first off, if you just let, just a second, buddy. Thank you. So, we can't, if we tried this, if you say, well, let's let u equal dx, then du would be, d squared x? Or I think it's dx squared. I mean, it's, right, don't worry about that. It would just be the second derivative of that, which, then how are you going to deal with that? When you go to put that, your minus v integral v du, whatever v happens to be, now you have the second derivative of that. Well, what does that mean? That's going to be hard. Like, so obviously that's not the case. The only thing you can do is this, which means everything else is going to have to go in here. Which is good, because you actually can take the derivative of this, right? Yeah, you can take the derivative of log x. It's just 1 over x. So that's nice. Now what about the antiderivative of dx? Well, it would just have to be x, wouldn't it? Right? So yeah, the derivative of x is dx. That's what we're calling it. So okay, all right. So now let's do this. Let's do the integral of that is uv minus the integral of v du. So uv is going to be x log x minus the integral of v du. And I didn't do my dx. Sorry about that. Oh, that actually works out really well, doesn't it? Like we could do this. X minus the integral. That's just a big fat 1 dx. So then the antiderivative should just be minus x. Plus a constant, but we don't care about the constant because we're about to evaluate this thing. But let's just make sure that when I take the derivative of this thing, what I get is log x. Because that's what I'm claiming, is that this here is the antiderivative of natural log x. So let's take the derivative here. So this is going to be a product there. Take the derivative of x, you get 1, leave the second part alone. Add that to, leave this part alone, take the derivative of that, that's just 1 over x. Okay? Minus, this just goes to 1, the c is a 0, and so we get log x plus 1 minus 1 is indeed log x. That is what we wanted. Okay, so now let's take this thing and evaluate it at the endpoints. So we are certain this is the antiderivative of that, and so to do the definite integral, we're going to evaluate this by e and down 1. All right. Now that constant's not going to matter, so it's going to be what happens when I plug in e minus off what happens when I plug in 1. Plug in an e, I get e log e minus e, constant, who cares? Plug in a 1. 1 log 1 minus 1. Now, log e is just 1. So this is e times 1 minus e. And this is log 1 is 0, so that's 1 times 0. That's just 0 minus 1 right there. E minus e is 0. Minus negative 1 is plus 1, and so it's 1. Right there, 1. So, in other words, the area under the curve of log x from 1 up to e, that area right there is a big fat 1. Alright, here's number 22. This is the integral of natural log y divided by the square root of y dy from 4 up to 9. So, again, if we try to use substitution, the only thing we could say u is equal to root y, okay, but then that means that log would have to be u squared, I guess. Does that make our lives easier? I don't know. It may or it may not. My intuition is, I'm looking at that and I'm thinking of this and I'm like, I don't know. That might make life easier, but maybe we'll just try a integration by parts here. Okay, so we need to find a u, we need to find a dv. Okay, so now don't let this denominator mess you up. In fact, the way that I think about this is that this is the same thing. I would just rewrite this. This is y to the 1/2 log like this. And so I could rewrite this as negative 1/2 log like that. That's how I'm going to rewrite this guy right here. Negative 1/2 natural log y dy. So this is what we're dealing with now. So u and dv. Now here's the thing. We could say, we could try this right here. But right away, like, I can't, I mean, we happen to know what it is now because we just did this example. But right away when I see this, I think, wait, the antiderivative of log, that's going to make my life harder. And knowing that the thing I'm about to do is this, thinking, well, if that's going to get more complicated, then I'm going to have an even more complicated thing in the integrand. So that's probably not the route I want to take. So I'm going to say let u be the log here, log y. So that du is 1 over y dy. Now the other stuff, and this is something we could take a fairly easily take the antiderivative of that guy. You would have to be, I guess, to the y to the 1/2 power, right? But then the 2 would have jumped down, so I guess we need a 2 there. That should do it. Let's just double check. Take the derivative of that thing, the 1/2 drops down and he's gone. Then you subtract off a 1 and you get that. Yes, so 2y to the 1/2. Okay, well, let's try it. Let's see what happens. uv minus v du. So uv, so that's 2y to the 1/2 log y minus the integral of v du. And now check that out. It's all just y's now. Much easier to deal with. So I'm going to pull that constant out front. v du, we have y to the 1/2 divided by y dy. Now all those pesky logs are out of our integrand. This should be easy to deal with. That's the same thing as y to the 1/2 over y, which should just be 1 over y to the 1/2, which is the same thing as y to the negative 1/2. And so 2y to the 1/2 log y minus 2 times the integral of y to the negative 1/2 dy. Hey, let's not use our brain. We already did this one. It's right here. The antiderivative of it is that. So 2y to the 1/2 natural log y minus 2 times 2y to the 1/2. That plus a constant. Okay, now I'm going to just double check this one. This is 2y to the 1/2 log y minus 2 times 2 is minus 4y to the 1/2. Oh, that's a constant. Now, let's check this and make sure that it works. If I took the derivative of this, we would have a product right here, minus 4 times whatever the derivative of that is. So here's the product. Take the derivative of that one. Leave this one alone. Add that 2. Leave the first one alone. Take the derivative of that. That's 1 over y. Okay. Now, this guy comes down. We get 1/2 y to the negative 1/2. That, hopefully, works out to that. Let's see. So, 2 and 2 is gone. We have y to the negative 1/2 log y plus 2, that's y to the 1/2 down here, minus 2 y to the negative 1/2 is the same thing as y to the 1/2 in the bottom. That and that are the same thing. That's y to the negative 1/2 times log y, which is the same thing as log y over y to the 1/2, which is indeed log y over root y. Okay, so that checks out. We checked it, we're good to go. So this is a definite integral. Let's plug in, let's evaluate it up at 9 and down at 4. So going to look something like that. Plugging in a 9, we get 2. 9 to the 1/2 is 3 log 9 minus 4 times 9 again to the 1/2 is 3. Plug in a 4. We have 2 times 4 to the 1/2 is 2 log 2 minus 4 times 2 to the 4 to the 1/2 is 2. So that's 6 log 9 minus 12. Yep. Minus 4 log 2 minus 8 is plus 8. So that looks like 6 log 9 minus 4 log 2 minus 12 and plus 8 should be minus 4, I think. 8, 9, 10, 11, 12. Yeah. So there you go. That's how it might look in the back of the book. They might have done something like this. Log 9 to the 6th power, log 2 to the 4th power minus 4, which that could be combined as log 9 to the 6th over 2 to the 4 minus 4. Any one of those look good. That's the idea. The only thing we haven't talked about in this section are reduction formulas. I just, in the interest of time, I'm going to let you read about that. There's one of the problems, number 45, says to use blah 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 like in example 6. Well, example 6 shows what a reduction formula is. I could just do it right here, or you could read it. It's about, it's very straightforward, and you'll see what's going on. But that's on page 493. Reduction formulas. Basically, we're reducing the power of something. It's the integral of sine to the nth power. So sine to the nth of something. And using integration by parts, which you'll see in there, and I hope that you work through it and actually do it, you'll see that you could reduce this. You'll turn this into a uv minus the integral of v du, and that v will have one less power. So you could reduce the, that's what it's called. It's a formula for reducing the power of one of these guys. And then I like problem 45 because it walks you through, some other stuff you could do with that. But that should be it. This will be due next time I see you, whenever that's going to be. We're all still very sick. So take care. Bye.